Hey everyone, welcome to the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I will gather them up and I will answer them here. And just remember, I record this show every Monday at 5 p.m. live. So if you want to be a part of the live show, you just got to go and show up on my YouTube channel, 5 p.m. Pacific time on Mondays. I'm recording this show live on Monday, May the 17th, 2021. So if anything really interesting happens over the course of this week and I missed it, that's because this show is up to a week behind. All right, let's get into this week's questions. Stephen Clooney. How do we calculate the age of the universe? If we can only see some part of the actual universe and the speed of expansion is accelerating, how do we accurately calculate the point of infinite density at the beginning? Thanks. So at this point, we know that the universe is approximately 13.7 to 13.8 billion years old, depending on which method you use to measure the age of the universe. And the different methods give you different answers. And for the longest time, this was like people thought, well, maybe it's somewhere between 10 and 15, 10 and 20 billion years old. But now we have a very accurate number. So how do we have such an accurate number for the age of the universe? And the answer is that we have a very precise measurement of the temperature of the cosmic microwave background radiation. And so I'll explain how this all works. So we know that the universe is expanding. This was the discovery that Edwin Hubble made when he looked at other galaxies, looked at the variable stars, measured the wavelength of the light that was coming from these stars, and noticed that they were mostly redshifted, which meant that they were mostly moving away from us. And as you look at various galaxies out there, you measure different amounts of redshift, and that roughly tells you the speed at which these galaxies are moving away from us. And so then it's kind of just like a math problem in reverse. You just take the speed that the galaxies are moving away from you, and then you just go, well, if they were a billion years ago, they would have all been closer, and a billion years ago after that, before that, they would have all been even closer and closer. And if you sort of do this backwards calculation, you ask yourself, at what point were all of these galaxies that we can see across the universe in roughly the same spot? That's the Big Bang. And it's a relatively complicated, but it's a calculation that they can do. And that's how they got this very rough number of like between 10 and 20 billion years ago was the beginning, was the Big Bang, was the beginning of the universe. So how do we get this very precise number? So the number that we got is the cosmic microwave background radiation, which is this afterglow that's left over from the Big Bang itself. And it was this time when essentially all of the matter in the universe was hot enough that it was kind of like the surface of a star, like a red giant star. And the temperature was sort of the same kind of temperature that you get if you're looking at the surface of a red star. And so it was opaque to light. And yet, when the temperature of the early universe cooled down to the point that light could finally escape, there was this very precise temperature that was. We've been watching the expansion of the universe. We've been watching those first photons get redshifted farther and farther apart until we see them today. And now today we see them as they're way off into the microwave spectrum. The temperature is like roughly 2.8 Kelvin, so vastly redshifted. And so you can essentially, once again, do the math. You know precisely the temperature as it is that you're looking at it today, and you know precisely what temperature it was when that light was released, you can calculate the difference and figure out how long the universe has been expanding and therefore learn how old the universe is. Now, astronomers have some other methods for measuring the expansion of the universe, and those give slightly different numbers. And so there's still kind of a bit of an argument about what is the correct exact number for the age of the universe, but roughly that's how they do it. The Hooded Crow. How stable is the current configuration of the solar system? Will the giant planets ever migrate again? At this point, the solar system is mostly stable. And the reason the giant planets migrated in the first place was because they were still scooping up dust. And so you had originally the nebula cloud where the sun and all the planets formed out of, and the star formed in the middle of this, and as it sort of all the material pulled in together, it spun up quicker and it flattened out into this disk. And then within the disk itself, the planets started to form, and they accreted larger and larger material, and then they started to spin up, and they started to pull in material from the cloud around them. And as they did that, they started to migrate around within this cloud. And eventually you got to the point where it looks like Uranus and Neptune swapped places, that all of the giant planets moved outward in the solar system. And this was really just in the search of a meal, the forces that were pulling them. And as you got sort of a difference in the distribution of the mass in the solar system, everything moved out. But at this point, here we are 4.5 billion years after the sun and the planets all formed, you've got a relatively stable situation. There's no more gas and dust really for the planets to pick up and change their distribution. The sun is roughly what it's going to be. Now, things may change a little bit by the end of the sun's life as it starts to bloat up and change its density. But for the longest time, everything is going to be fine. That said, there still are tiny little interactions, tiny instabilities in the solar system. And I've heard it said that there's like a 1% chance that Jupiter, for example, could kick Mercury out of the solar system through the interactions of its gravity. So, over time, or throw it into the sun. And so there's like tiny little oscillations that could build up. But I mean, here we are 4.5 billion years after the formation of the sun and the planets, and everything is roughly stable at this point. Larry Beckham. Hey, Fraser. A question has popped in my brain. After OSIRIS-REx spacecraft discharges its valuable cargo in the Utah desert in 2 years, what then for this iconic traveler? It will have some fuel left. Will it still do something interesting? Yeah, so after OSIRIS-REx finishes its mission to deliver the sample cargo that it brought back from Bennu back here to Earth, it's going to do a quick flyby of the Earth, and then it's going to go back off into space. It's still going to have some propellant on board, and it's still got solar panels and the capability to do other things. And so at this point, NASA will give it some kind of extended mission, probably give it some other target to go after, either to do a flyby, or maybe if we're really lucky and the orbits work out, that it could actually do some kind of orbital mission around another asteroid. Of course, it can't retrieve another sample, so it's never going to be able to do that again. But we could get future either multiple flybys or one final home for OSIRIS-REx, or maybe they'll crash it into something. But usually in these situations, NASA comes up with another idea for what to do with the spacecraft. Jeff Sonderman. Hey Fraser, what are the next frontiers for gravitational wave astronomy? Will we get better detectors, and what might they discover beyond the black hole or neutron star collisions that we've seen? The age of gravitational wave astronomy has really just begun, and of course, the big thing was to find these giant black hole collisions of intermediate, sort of large stellar mass sized black holes. And of course, now we've also seen possibly a black hole collide with a neutron star. We've seen the neutron star collisions. So then you're going to go in both directions. You're going to have collisions between, say, white dwarfs, which are probably happening across the universe as well. We're going to have collisions between much larger, supermassive black holes. We're going to get possibly like the gravitational waves from a supernova that is asymmetrical. And so if the supernova blows off in one direction and does this wobble as it explodes, we should be able to detect those. And then we're going to be able to detect over time these objects as they're farther and farther apart. So right now, when we detect, say, two black holes about to merge, we only detect it, say, in the last minute before the black holes merge together. But imagine if they're farther and farther apart, and maybe we can start to detect them when they are hours apart, weeks apart, days apart. So that's pretty exciting. Then the other thing that we're just starting to get now is this idea of a gravitational wave background radiation, sort of in the same way that we have the cosmic microwave background radiation, that there's the potential for just different wavelengths of radiation. We could get, and it's possible this has already been detected, that there's already this gravitational wave background that we're already seeing, where you've got these black hole collisions happening across the universe, and now we're starting to see the ripples just bouncing around and moving around in space. This is being done through pulsars, and so astronomers have been watching with the Gaia instrument. one of my favorites. They've been watching the positions of pulsars and watching how the pulsars are bobbing back and forth out there in the universe, and they're detecting these large scale gravitational wave background information. And then the one that's really like the most exciting is to be able to detect the primordial gravitational waves. So if you could go right back to the beginning, before the cosmic microwave background, right back to the very Big Bang, when the universe was forming and you had various kinds of masses moving around at high speed velocities, you should expect some kind of gravitational waves being generated by all of this material as it's moving around. And that would answer so many questions. It would directly tell us the age of the universe. It would give us maybe a hint of what came before the Big Bang, whether the inflation theory is the right one, or maybe if there's other theories that work better, were there primordial black holes present at the beginning of the universe. And so there's so many other things that gravitational wave astronomy is going to do. We are just, it's like someone just handed us a brand new scope. This is like Galileo pointing his telescope at the sky for the first time. You know, his first telescope was like 9 power. And he was able to see the rings of Saturn, the moons of Jupiter, the fact that Venus goes through crescent phases, was able to see that the Milky Way is made of stars, was able to see the craters on the moon. This is where we are with gravitational wave astronomy, and it's just going to get better and better and better. Sid Parashar. As the sun is getting hotter day by day and Earth's temperature is rising too, is the Goldilocks zone shifting? If yes, will the shifting Earth by thousands or millions of miles solve the problem? Now, again, we talked about this a couple of weeks ago. Yes, the temperature of the sun is increasing, but the temperature of the Earth, thanks to the sun, is going to increase by about 50 Celsius over 1 billion years. 1 billion years. So it has no impact on global warming. But in the end, it's going to doom the Earth long before the sun actually turns into a red giant. And so, yeah, over time, the Goldilocks zone, the habitable zone of the solar system, is shifting outward. And so right now, it extends from Venus through Earth out to Mars. And in the future, it's just going to keep shifting outward. And eventually, even Earth will no longer be in the habitable zone of the sun. And the solution is, yeah, you could move the Earth outward from the sun bit by bit. I think the calculation was to have an asteroid come close by the Earth once every 10,000 years or so and shift its orbit out just a tiny little bit. And you would be able to compensate for the increasing temperature that's coming from the sun. And that would let you go all the way out until the point the sun becomes a red giant, and maybe even after that. So if we could master that technology, it would buy us another 4 billion years of nice temperatures orbiting around the sun. Strange Quark Star. Distant future civilizations will not see the cosmic microwave background radiation and won't know about the Big Bang. Are there already things that we have missed finding out about? Would we know? That's a really good question, and I don't know the answer to this question, but I want to talk about it because I really like this idea. So because the universe is expanding, we're going to get to this point in the far future where all of the galaxies that are not collected gravitationally to us in our local group are going to fall over the cosmic horizon. They will essentially be moving away from us, from our perspective, faster than the speed of light. And their wavelength, instead of just like disappearing, their wavelength will just stretch out and out and out and out. And eventually they'll move into the microwave, they'll move into the radio spectrum, longer and longer wavelengths of radio spectrum. And so it wouldn't be initially obvious right away that there are galaxies out there. And so for future, it's about 100 billion years from now. And so if you're aliens living, and that's, if you live around a red dwarf star, that's not forever. Red dwarf stars will last for up to 10 trillion years. And so astronomers who were born and raised around a red dwarf star may look out into the universe and not see any other galaxies. And so they wouldn't think that there was a set time that the universe formed. But the answer is actually not that simple, because if future civilizations were able to create some kind of radio instrument and watch the sky, they would detect some kind of signal that told them that there was some kind of expansion that was going on. And it might be that they'll have to make really, really powerful radio telescopes that can handle very long wavelengths that are hundreds of meters long. But there still would be this very faint signal that they probably could detect. And then from there, they could probably deduce that they are living in an expanding universe and try to calculate when the universe itself formed. It just won't be as obvious. So that detection might come thousands of years later than it did for us when they built this galaxy spanning civilization, and they've got these incredibly powerful telescopes, and they notice this weird signal that's out there. So it's not kind of as simple as that. But then the question is, like, are there things that we won't see? I mean, right now we're so early on in the age of the universe that there aren't things that are completely gone from our perspective yet. But there are things that we've missed. Like, there was a time in the early universe, about 13 million years after the Big Bang, when the entire universe was room temperature. That the habitable zone was everything, which is sort of a cool idea. A couple of billion years after the Big Bang was actually the height of star formation, the time when the most stars were being formed, when the universe was having its party. And here we are, 13.8 billion years after the universe formed, and star formation is down to just a couple of new stars every year in the Milky Way. That's amazing to think that there was a time when it was vastly faster, that there's furious star formation going on in all of the galaxies across the universe. And now things are relatively slowed down now. So I think, maybe in other wavelengths, like maybe if you listened in gravitational waves, the universe would have been louder early on, and now we can just barely detect it. So maybe that's a good analogy. But I don't know. I mean, if you're watching this and you have some ideas, and put them in the comments, because I love the idea of, one of the really weird coincidences is that we exist at a time, if the universe is going to last for an infinite amount of time, from when it formed to when the last, it will never, it will continue to expand, accelerate. And yet here we are at a point that is closer to the beginning. It's a weird coincidence. Now, of course, if you think of it sort of from an anthropic perspective, we could only appear at a time when the universe was closer to its formation, when there was adequate energy to form planets, life, etc. But still, as coincidences go, the fact that the moon and the sun are the same size in the sky is a coincidence. And the fact that we're present early on in the age of the universe, when it will have eventually probably infinite time, is interesting. Nothing else about that. It's just kind of fascinating. More questions in a second, but first I'd like to thank our patrons: Stan Senkowicz, Michael Friedman, Bill Christian, Craig Landon, and the rest of our 836 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universetoday. Avi Scott and Flower. Could a powerful enough telescope ever look beyond the CMB? No. No matter how powerful a telescope you have, you could never look beyond the cosmic microwave background radiation, because the cosmic microwave background radiation is a time where every single place in the universe looked like the surface of a star. And so if you wanted to go and look at the sun, you'd be asking yourself, can I look through the sun? Don't try. You don't want to do it, right? The sun is opaque to your telescope and would light your eyes on fire. But let's say the sun was a red giant and you tried to look at the sun with a telescope or some kind of sensor. You would see the surface of the star, and you wouldn't be able to look behind it because the star is a mass of incandescent gas. It is a ball of plasma, and the plasma is opaque in the same way that a wall is opaque. And yet every single part of the entire universe was opaque. And when you're looking at the cosmic microwave background, this time that's like 380,000 years after the Big Bang, you are seeing that in every single place that you look. It's the farthest we can see back. And so no matter how powerful your telescope is, right? If you can look at a wall, no matter how powerful a telescope is, you're still just going to see the wall. And so we need other methods to be able to see beyond the cosmic microwave background. And the only two methods that we know of that were possible was gravitational waves. Gravitational waves were present earlier on in the universe, and probably neutrinos. Neutrinos were present earlier on in the universe, and they were able to escape out into the rest of the universe. And so with really powerful gravitational wave observatories, we should be able to see right to shortly after the Big Bang. And with really powerful neutrino observatories, we should be able to see right to the beginning of the universe. But with regular visible light, with the electromagnetic spectrum, we will always be blocked by the cosmic microwave background. Andrei Zalukhanov. What if there's no mid-state between planet civilization and some advanced civilization? If we invent something like intelligent AI, it could make the fast transition to something like a planetary-sized mind. It's a great question. It's sort of an interesting thought experiment, but it's actually more terrifying than you think, more troubling. There's this idea of artificial intelligence, idea of von Neumann probes, that we eventually build self-replicating robot probes. We send them off to other star systems. They build more copies of themselves. They go off to other star systems and continue on outward into the universe. And then there's this idea that if we build artificial intelligence here on Earth, then there's this idea of the fast takeoff, that if we can teach an artificial intelligence computer to make a better version of itself, it does so, and then the new version makes a better version of itself. The new version after that makes a better version of itself, and just goes faster and faster at an exponential rate. And they call this the fast takeoff. You're essentially reaching the singularity, this point to which we can't even imagine what the future looks like after we've taught robots to build other robots. And as an advocate who wants to see robots build other robots, maybe I should rethink my position. Anyway, so we'll put these ideas together, and you get this situation where if you develop rapidly expanding artificial intelligence and it's trying to make itself better, then the most useful thing that it can do is essentially turn the entire Earth into one computer. Perhaps there's like the ideal computing substrate. This has been known, it's been called computronium. So whatever is the best way to organize matter to compute. And of course, we can harvest energy from the sun. We've got the rest of the planets in the solar system. And so after the Earth has been turned into computronium, you gather up all of the planets, asteroids, objects in the Oort cloud, etc., turn them into more objects of computronium. Maybe it makes the most sense for cooling to have small objects. Maybe it makes sense for speed, for the speed of light, to have one giant object that is able to compute. We don't know. The computers will figure that out. And then they build seeding probes that head off to other star systems to do the same thing. Maybe they try to bring the resources closer together. Maybe they make sense to leave them farther apart. And eventually you get this situation where you've got these von Neumann probes. You've got this artificial intelligence civilization that's expanding outward from wherever was the beginning point at as close to the speed of light as it possibly can. And that allows it to reach about 4% of the observable universe. So you can reach, although we can see the entire universe, only 4% of the universe is reachable. And so these artificial intelligence would realize this, and they would hustle to get as close to the speed of light as they possibly could and try to grasp at all of the resources within this sphere, the reachable universe, and turn it all into computronium, whatever is the most efficient method of computing. So that. Corey S., is the cosmic microwave background receding away from us? Does it change over time? The cosmic microwave background is receding away from us, and of course it's like the most distant thing we can see. So if some of the galaxies are moving away from us faster than the speed of light from our perspective, the CMB is moving even faster. It's like the maximum redshift. But the part that's kind of crazy is that every second that goes by, and you're seeing the CMB, you're not seeing the same cosmic microwave background. You're seeing the next moment of the universe, the moment that light was escaping from every spot in the entire universe. You're seeing that second of this light escaping, but it's for a new part of the universe that's a little bit bigger. So imagine, 1 second later, you're seeing a new part of the entire universe suddenly being lit. And then 1 second later, you're seeing a little bit more of the universe. And the part that you saw before, that light has already gotten to you. And so you're not seeing that anymore. So whenever we see the CMB, we're constantly seeing, you just watch it, you're constantly seeing farther and farther regions of the universe that are letting off that first light. It's sort of wrecks your brain to try and think about it. Mark Elkin, should we pay bounties to remove space junk? Removing space junk is going to be a big problem. It's sort of this kind of crazy idea that right now there's no worldwide regulations for space junk. If you launch a satellite into orbit and then you put it on a really nasty orbit that's going to interact with a lot of other satellites, it's going to stay up for a very long time. There's no rules to stop you from doing that. Now, if your satellite deorbits and it's too big and it crashes into the Earth and it hits somebody's house, you are liable. But if you launch a satellite and it smashes into someone else's satellite and destroys it, there's no repercussions yet. So our laws for space junk are way behind where they need to be. And right now, you can launch a satellite, you can leave the upper stage just in orbit, and it can just fly around, and you don't care where it is and what it's going to interact with. And with all of the satellite constellations that are going up, with all of the human spaceflight that's going to be happening, with space, especially near space, is becoming a more and more precious resource. And so we're going to need to get into this age where people have to have this birth to death management of anything they launch into space. Like if you're going to launch something into space, you have to have a plan for how you're going to bring that spacecraft down at the end of its life. Either you launch it into a very low orbit where it's constantly interacting with the atmosphere and it's only going to stay in space for a few years, decades at the most, and then it's going to deorbit itself just through friction with the atmosphere. Or you have some kind of mechanism on board the satellite that's going to allow it to deorbit. A tether, a drag sail, a retro rocket, something that when you're done with it, it's going to crash itself back into the atmosphere. And I mean, there are already tens of thousands, hundreds of thousands of pieces of junk in space, or working satellites, from working satellites to astronaut gloves to spent boosters to pieces of paint. It's all up there and it's all moving at tens of thousands of kilometers an hour. Each one is like a little bomb that's going to hit something else and detonate it. And so we need to take this more seriously. It would be really tricky to set some kind of bounty to retrieve space junk. The problem is that in order to retrieve a piece of space junk, you literally have to fire off a rocket mission. Like say there's an astronaut glove that you want to retrieve because it fell off the International Space Station and it's orbiting around the Earth at 28,000 kilometers an hour, and you want to retrieve that glove. All right. So you've got to make a spacecraft. So say the spacecraft's going to cost you $50 million, and you've got to launch it on its own rocket. Say you're going to go with a Falcon 9. So you're going to pay about $60 million for the launch. You're looking at, say, $110 million, maybe $150 million to sort of balance it all out, to send it into precisely the orbit so that it can reach up and catch onto the astronaut glove and grab it. And then the satellite that you sent and has to be able to then deorbit itself to bring that astronaut glove back into the Earth's atmosphere. So it's got some kind of drag sail or some kind of tether that it puts out. You did it. So you got rid of one piece of junk for well over $100 million. Now do that 100,000 times. like this problem is we're well beyond simple solutions to this problem. Now, the idea that I like the best is this idea of like a really powerful orbital laser that shoots pieces of space junk as they go by and ablates a little bit of material off of the space junk, providing a little bit of thrust and causing it to deorbit itself. And so as a piece of space junk goes past the laser, it shoots it, goes zap, 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 and the piece of debris gets these little deceleration bursts that causes it to lower its orbit and eventually crash into the atmosphere. That seems like the only way en masse to deal with the space junk problem in its current situation. But definitely not launching any more junk into space is a really good start. And I'm sure within the next couple of years, we're going to see some kind of global treaty that defines the rules and regulations for launching stuff into space. But it's the same thing with like deep sea. Like once you're outside of the coasts of various countries, there's no rules. There are some rules, but there are less rules, and space has less rules than that right now. You know, mostly people are focused on don't put nuclear weapons in space where you can destroy your enemies instantaneously. Give them an hour's notice as the ICBMs fly across the planet. So yeah, space junk is a big problem. It's getting bigger, and people need to take it more seriously. Jonathan Allen, would there be a use case for launching rockets from Canada, or is it just wishful thinking on my part? No, there's a very good use case for launching rockets from Canada. So the main launch orbit that most people want is they want to go into, they want to launch from the equator. And the reason you do that is because as you launch as close to the equator as possible, you get this speed boost from the turning of the Earth. It allows you to either launch with less fuel, with less propellant, or allows you to launch a heavier payload with the same amount of propellant. But there are different kinds of orbits. And so one of the orbits that is incredibly useful is this idea of a polar orbit. So instead of launching around the equator of the Earth, you want to launch around pole to pole. And when you do that, when you go in this polar orbit, then what happens is the Earth is essentially turning underneath your satellite as your satellite is going around. If you time things right, you get a view, you come around, and then the Earth is turned a little bit more, and you get to come around, the Earth is turned a little bit more, and you get this view where you can make this really comprehensive scan of the entire planet. And so polar orbits are very useful. And those are launched nicely from Canada. And so there are plans to potentially build a spaceport out in Nova Scotia. So we might very well see rocket launches happening from Canada. I think that's one of the things that's interesting now. We're seeing more and more spaceports getting built in more countries. Like back in the olden days, you had Florida, the Baikonur Cosmodrome, and that was it. And now we've got in China, in Japan, a couple of them in Russia, a couple of them in the United States, New Zealand, and potentially we're going to see Wallops. You got several rocket facilities in the US, South America. And so over time, we're going to see more and more of these ideas. But yeah, polar launches are a thing, and they're very useful. There's other orbits as well. There's like a Russian one they use called a Molnier, which is sort of acts like a geostationary satellite. So you can get, but it's on this really long elliptical orbit where it brings the satellite back. So it sort of, for part of the time, appears to be hovering over the planet, but then the rest of the time is sort of on this long orbit, and it allows you to sort of see the same spot of the Earth on a regular basis. So there's a lot of good orbits, not just equatorial orbits. Well, thanks everybody for asking your questions this week. This was a lot of fun. As always, if you're watching this anywhere across my channel, or if you're watching any of my videos and a question pops in your brain, don't hesitate. Just write it down. I read all of the comments and I answer many of them in the chat. But if you want to watch the show live, join me every Monday at 5 p.m. Pacific time on my YouTube channel and just hang out with me live. And also, the show is about 3 times longer, 2.5 times longer than the one that you see, the final edited version. So if you want more space stuff, you should join the live show. If you want a single comprehensive resource for space news, you'll want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights about the story, and links you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all of my videos are also available in handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to all the moderators, and a special thanks, as always, to Chad Weber and Nancy Graziano.